Well, hello everyone. My name is Erick Martinez. Ríos. The title of my presentation is Feature Extraction of Vehicle Vertical Acceleration Signals performed through the Wavelet Scattering Transform and Machine Learning for Pavement Transverse Cracking Detection. I am from Tecnológico de Monterrey. And well, so the outline of this presentation is as follows. First, I will make a brief introduction about the topic. Then I will talk about the literature, the problem statement, the methodology, the results, and the conclusions. So first of all, it is important to know that road surface anomalies are any deviation from the regular road conditions. These anomalies can include the potholes, cracks, and routing. And the traditional way in which the road surface anomalies are evaluated is through pavement condition index surveys. Nevertheless, this method is sensitive to human errors, may risk the road technician's health, and is considered time-consuming. And based on these problems, in the literature, we can find works that have tried to detect these road surface anomalies without human intervention. And one of the approaches is to use the vibration of the vehicle to classify or detect these road surface anomalies. In this case, we can find works that have tried to use feature extraction with machine learning, for instance, using time and frequency domain features. Also, we can find articles that use threshold values. They basically monitor an amplitude change in the signal or crest factor. And if it exceeds a predefined value, they classify that as an anomaly. And also, there are works that use deep learning. For instance, one of the most common techniques that are used in literature are the convolutional neural networks. But what is the problem of all of these solutions? Well, if we use threshold values, well, we need to an adequate and constant calibration of this threshold value. If we use feature extraction, we require domain knowledge about the data set. And in most of the cases, the selection of the features, either they are computed in the time or frequency domain, they are selected arbitrarily, or the authors use trial and error to compute the features and then use that features to train the classifier. And in the case of deep learning, well, you need large sample sizes, high computational power, large training times, and also these deep learning techniques, for instance, convolutional neural networks, are considered black boxes. So if you want to understand what is the relationship or the mechanisms in which the algorithm is making a classification, well, it's quite complicated due to the complexity of these models. So based on these approaches that are already available in the literature, what we proposed was to use the following methodology. In this case, we were using vehicles vertical acceleration signals. And instead of using feature extraction in the time and frequency domain or use deep learning, what we proposed here was to use a technique called the Wavelet Scattering Transform. And we apply this technique to the acceleration signals. And based on this transformation, we trained 4 machine learning classifiers. We decided to use the most simple ones, like a linear discriminant analysis, a super vector machine, a decision tree, and a can-nearest neighbor. And we compared the performance of using the scattering transform as a feature extraction technique and these 4 machine learning classifiers using 5-fold and 30-fold cross validation. And the classes that we compared were the cracked asphalt pavement and the uncracked asphalt pavement. So in this case, we were using a public available data set that was collected by an author named Xu, that is a reference for this presentation. This vehicle vertical acceleration data was collected from one single vehicle, and the accelerometer was placed in the tire suspension knuckle of the vehicle. These are the dataset characteristics. One of the highlights of this dataset is that it is relatively small. We have a total of 327 signal segments. And the distribution of the dataset was as following. Of this sample size, the 33% were signal segments associated with pavement transverse cracking. and the 67% of the signals were associated with uncracked pavement. So talking a little bit about the feature extraction technique that we use for this work, this is called a scattering transform. Basically, well, this was proposed by an author named Stefan Malat, and the main question that he wanted to answer when he developed this technique is how signals should be represented for classification. So his idea was to create a representation that has two properties: invariance to translations and stability to small-time wrapping deformations. And if we achieve these two properties, maybe we can reduce the within class variance of the set of signals, and maybe we can apply a linear classifier that can help us to discriminate between the two signal segments. And contrary to other signal representation techniques like the Fourier transform or Wavelet transform, well, in the case of the Fourier transform, the magnitude of the Fourier transform is translation invariant. But the problem is that it is not stable to small-time wrapping deformations. And the Wavelet transform is translation covariant. So neither the Fourier nor the Wavelet transform are adequate if we want to create this representation that is invariant to translation and also stable to small-time wrapping deformations. And basically, the scattering transform, what it does is to compute a cascade of convolutions through wavelets, nonlinearities through modulus operations, and pooling through the scaling functions. In fact, the architecture is quite similar to a convolution neural network. The difference is that in this case, we are not learning the filters. We are fixing the filters, and in this case, there are wavelets. We predefine these wavelets. They are modeled wavelets. And also, we are not guessing the nonlinearities. They are basically modulus operations. And this scattering transform is composed of three main parts. We have the zero order scattering coefficients, the first order scattering coefficients, and the second order scattering coefficients. Basically, to compute the first order scattering coefficients, we apply a wavelet transform to the input signal, we apply a modulus to the results, and then we apply another convolution with a scaling function that is basically a low-pass filter. But this cascade of convolutions, what basically does is that they progressively translates the higher frequencies to lower frequencies, and in this way we can achieve this invariance to translations and stability to small-time wrapping deformations. This is an example of the results that we obtained after applying the scattering transform to the vehicle vertical acceleration signals. In blue, you can observe the scattering coefficients of a signal associated with transverse cracking. And in red, you can observe the scattering coefficients of a signal associated with uncracked pavement. In this case, well, these were basically the features that we used to train the classifiers. And as a first analysis, we performed five-fold cross-validation using a linear discriminant analysis, where we obtained a sensitivity of 67%, a specificity of 78%, an F1 score of 63%, and an AUC of 80%. For the case of the support vector machine, we obtained a lower sensitivity of 46% and a specificity of 94%, an F1 score of 59%, and a validation AUC of 81%. For the case of the decision tree, we obtained a sensitivity of 44% and a specificity of 89%, an F1 score of 52%, and a validation AUC of 73%. One of the last classifiers that we tested was the Canivers neighbor. In this case, the Canivers neighbor gave us a sensitivity of 50% and a specificity of 88%, an F1 score of 57%, and an AUC of 67%. Here in this figure 4, I'm showing the validation receiver operating characteristic curve of each of the classifiers when performing five-fold cross validation, and also you can observe here the AUCs of each of these rock curves. And as we can observe, for most of the classifiers that we tested, for each of the cross validation folds, the AUC is better than compared to the random classifier curve. Another test that we compared was to compute the AUC of the classifiers trained with the scattering transform features using a dirty fork cross validation. In this case, we observed that the average sensitivity was better for the linear discriminant analysis compared to the other classifiers. And also, as I mentioned before, we compute the average validation AUC, and we obtain the following values for each of the classifiers. And we compare the average validation AUC obtained for each of the classifiers using a ANOVA test and a multiple comparisons test. This is basically the distributions of the average AUCs when performing dirty fork cross validation for each of the classifiers, the linear discriminant analysis, the super vector machine, the decision tree, and the Canivers neighbors. And we performed the ANOVA test and the multiple comparisons test. And what we found out is that the only classifiers that show a difference in their AUC, in their average AUC, was the super vector machine and decision tree. But for most of the cases, there was not a statistical difference between this average AUC obtained for each of the classifiers. And also the decision tree was the classifier that gave us the lowest performance compared to the others. So, well, as conclusions, in this work, we propose to use the scattering transform as a feature extraction technique for pavement transverse cracking detection. The results show that the linear discriminant analysis trained with the scattering coefficients attained the best performance with an average validation sensitivity of 67% and an average validation AUC of 80%. For the case of the dirty fork cross-validation results, show that the linear discriminant analysis performed better in terms of sensitivity with a value of 68% than the other tested algorithms. And finally, the super vector machine achieved a higher value regarding the average validation AUC for the dirty fork cross-validation process. However, the multiple comparisons test showed that there was no statistical difference between the average AUC of each of the classifiers when they were trained with the scattering transform coefficients. These were the references that I used for this presentation, and thanks for your attention and time.